Hello. Welcome back to the continuing lecture in return on investment. And today's topic is the geometric average. So actually, this is a topic for this segment of the video, but we've been talking about the different types of averages for the last, couple of videos, right? Or last couple of segments. Now, so today uh, it's time to talk about finally get down to the real McCoy part of this uh, lecture or the first topic. So, what is geometric average then? Now, let's think about let's go back to this house value example and think about the growth in the house values, right? And the reason for talking about the geometric average is because the simple average is not the right way. Okay, so to annualize or to take the average of the total return or total growth over the last during the holding period, right? And in this example, the holding period is 11 years. And the reason that, and I told you, if you, in our last video, I said simple average is not the right thing. Why? Well, because if you divide, let's say 233%, which is the total return during the holding period or the holding period return, if you divide it simply by 11, you are completely ignoring the fact that this is the growth in a house value, a single house, right? The value of the single house over 11 years. In other words, there's a time dimension. This is about the growth of the house value over time, right? So let's think about it. Why, in that case, you cannot use the simple average? Now, think about it. If you're measuring your, let's say, over the last 5 years, you marked, your height, right? You're now like 20 years old, and since the end of your 15th birthday, since your 15th birthday, you checked your height. You marked it on the door frame or on the wall every year. So on your 15th birthday, you were 5'5". On your 16th birthday, 5'6", and so on. Each year, your height is different, and of course, some years, the growth is uneven. That's natural, right? The growth cannot be even. And also look at these house values. They are uneven each year. The growth in house value is naturally, right, supposed to be uneven. Now, and if you are supposing when you on your 20th birthday, right, you are 6 foot. Let's say you're 6 foot, right? What does that mean? Over the last 5 years, you grew 7 inches, right? You grew 7 inches. So then, how would you then, find the average growth rate or average growth, per year, what do? You divide it. I mean, of course, by inches, you can do that. And by inches, right? How many inches per year? You can divide it by uh, 5, right? But in terms of growth rate, so what is the percentage of your growth each year? You cannot divide it by 5. Why? It's like this. The reason is, first of all, let's take a look at what the growth rate means. What is the growth rate? Let's take a look at the growth rate between 2015 and 2016. I mean, the capital gains between these 2 years was 86,000. Isn't that right? Yes. So basically, the growth rate, the growth portion in the house value is 86,000, and the base level was 414K. That was the base number between the 2 years. And then the growth rate can be calculated by dividing the growth portion, right? The portion of that portion that is the result of the growth, and the base level. And by the same analogy, you can do the same thing between 2006 and 2005. So it's not 2 years, it's 1 year, because it's between the end of 2005 and the end of 2006. Make sense? So it's the same thing. The growth was, and I already calculated the capital gains, which is the growth portion, right? You divide it by the base level, right? The previous year's, previous year is the base for each annual growth, right? So then in the first year, it was 20%. And because the formula is the same every year, you can just copy and drag it all the way up, right? Now think about it. And in the so in the first year, the growth was this. So in 2006, this was the house value, right? And then in 2007, this is the house value. Actually, the growth was negative. So there was a capital loss. And then, in 2008, the growth was like, 52,000. But now think about it. This 18,000 is the result of the growth from 15,000, right? It's the result of 20% growth in terms of percentage, right? It's the result of 20% growth, right? And then this 163,000 is the result of the negative growth from 180,000, which is the result. Which is the result of the growth from 2005. Make sense? In other words, there's a like a chain reaction, right? Like a chain reaction. You cannot have 2007 house value without the growth from 2006 house value, which is not possible without 2005 house value. In other words, I called it chain reaction, but it's called also correlation, right? I mean, this is not really the correlation in it's autocorrelation. I mean, correlation is usually used in the context of different variables, but this is one variable, right? Think about it. One variable. This is the change in house value of a single house, one particular house, not different houses, right? Not many different houses, right? So the growth of each successive year house value in each successive year is the result of the growth from the previous years. Make sense? So in other words, final 2016 house value is actually the result of the growth from 20.77% growth from 2015 house value, which is the result of 0% growth from 2014 house value, and which is the result of the growth from 16.29% growth from 2013 house value, and so on. You understand what I'm saying, right? It's the result of the long chain of autocorrelation, right? Now, this type of process that's going on here is called compounding, right? You understand? What is compounding? Compounding is like, a successive chain reaction that is, getting compounded. It's like, suppose you made a snowball. Suppose you're standing up on the top of the snow-covered mountain, and you picked up some snow and made a snowball and dropped it on top of the mountain. Now what's going to happen? The snowball will roll down the mountain, and as it rolls down, right, the snowball will get bigger and bigger and bigger and bigger, right? Makes sense? As the revolution per each but the rate of growth is not constant, right? The rate of growth, if you think about it, the rate of growth each time it makes a revolution, right? The rate of growth is increasing. Make sense? Why? Because the surface, as the snowball rolls down the hill, it picks up more snow and more snow because the surface area of the snowball gets bigger and bigger. And with a larger surface area, bigger surface area, the amount of snow it picks up will increase. In other words, it will accelerate. You understand? The rate of snow growth rate of the snowball will accelerate. It won't be constant. Even at a constant rate, the snowball eventually will get huge by the time it reaches the foothills or the bottom. When it touches the level plane, right? It will get huge. But the idea is the size of the snowball will compound. Make sense? It's the same concept. At first, the 2005, beginning with the 2005 house value, it grows by 20%, and then that will grow by negative 9.44. That's getting smaller. But then that will grow by 31, almost 32%, and that will grow again by 18, 19%, and so on. Make sense? So when there is a compounding going on, and the compounding happens through time, so there is always time dimension, right? Compounding is something that happens over time. In other words, in a static picture, there is no compounding. It's only through in a dynamic time dynamics, right? Over time, compounding happens. So you get the idea. What I'm saying is, let me go back to then the slide. Quickly go back to the slide, and let me, okay. So let me switch to the slide. Okay, so here's the idea of compounding. So what do you see here? So so this looks quite complicated. So let me get down to but that's the same. It's the same language. Finally, I mean, 2016 house value is the final house value, right? But it starts from 2005 house value. It grows by what 1.1 plus growth rate in year one. And the growth rate in year one was like 20%, wasn't it? Something like that. And then if you multiply 2005 house value by 1 plus first year growth rate in year one, then this will become what? 2006 house value. But then if you multiply it by 1 plus growth rate in year two, what does it become? It becomes 2007 house value. And this is 2007 house value. And then you multiply it by 1 plus growth rate in year three, and then 2008 house value. If you keep going on like this, and by the time you compound it, like by 1 plus growth rate in year 10, and then that's going to be 2015 house value. And then you multiply it by 1 plus 11 growth rate in 11th year, it will become 2016 house value. And that's exactly explained here, where if you rewrite it, 2016 house value is 2015 house value times 1 plus G11, which is, basically 2005 house value times 1 plus growth rate year one, in year one times all the way through 1 plus, times 1 plus growth rate in year 11. Okay. I mean, this is, finally we arrived there, but starting from 2005 house value, if you compound it by 1 plus growth in year one, that's 2006 house value. And then 2006 house value times 1 plus growth rate in year two, then that's 2007. Whereas, where that 2006 house value is the result of actually 2005 house value times this, and then 2007. So this is 2006 house value. 2007 is 2006 house value times 1 plus G2, which is this, right? In other words, if you break it down, think about it. P 2006 is actually replaced by this, by its own definition. What is the P 2006? Its definition is P 2005 times 1 plus G1. That's 2, right? So I simply replace this by its own definition, right? But we are talking about 2007 house value. So 2007 house value is 2005 house value, right? Times 1, which is, this, 2000, house value 2006 times 1 plus G2. So this is, basically what is the chain reaction that is going on in that the process, right? This is the process that's going on in there. So if I get back to, let me stop the, the PowerPoint and go back to the Excel. So now, if you're back in Excel, now let's think about it. Let me move this around, and so we can use that space. Yeah, I'll just put it here like this. So let's think about it. I'll copy this. So let's find if, and then you see what I put here. That's 1 plus growth rate. 1 plus growth rate. Okay. And then for each year, I will find, I can copy and drag it down and find 1 plus growth rate for each year. Then let's think about it. Starting from, see if I can replicate the house values from here. So let's think about the 2006. What's the house value in 2006? We know it is 180K, but that is the result of 2005 house value times 1 plus G. This is already 1 plus G. This is G1, right? 20% is G1, growth rate in year 1. And I exactly replicated house value. And then suppose, I just drag it up all the way. What do you see? Didn't I replicate all the house values there? In other words, this proves that the house value each successive year is the result of the growth from the previous year, right? And then in so when there is this proves that there is when there is compounding going on, the average growth rate, so these are the growth rates, and if you think, oh, if I take the average of that, let me take the average. Simple average, you simply add them up and divide it by 11. That simple average doesn't do the justice. Why? And here I got the arithmetic average there, which is what? Simply, taking the average there. If you take the average, simple average is 12.21. But that is wrong. I've been telling you that's wrong. Why? Because it's ignoring that compounding effect. It's ignoring that compounding effect. So in other words, it is overstating. The simple average will be overstating the actual average growth rate, because each successive year's growth rate is getting a boost from the previous year's growth rate. Make sense? If it is getting a boost, right? That boost is coming from that correlation, successive correlation. And simple average is the one that is used when there is no correlation between each other. When there is no, correlated boost from the previous year. You understand? You can use, so if I take the geometric average, it's actually 11.57%. And this is how I take the geometric average. But you can tell, oh, so the arithmetic average or simple average is overstating the actual average growth rate. Make sense? Now, the reason is, as I said, you can use simple average in a situation like this. Suppose I'm taking the average height of the people in this class. And let's say there are 25 people in this class according to the roster, right? Usually in a face-to-face class, there are roughly 30, give or take a few people. But if there are 30 people in the classroom, to take the average height, what would I do? I will first get the individual data point. Isn't that right? I will measure heights of each individual. There will be 30 data points then. And then I can add them up, divide it by 30. Why? Because your individual heights are not correlated with each other. There's no time dimension here. Isn't it right? Your heights are all taken at the same point in time. So it's static in time. But if I'm measuring your height over the last 5 years, and I pick one individual and I observe that individual since 5 years ago, measuring height each year, collected 5 years worth of data. So that's like 5 data points. And then of course, how many inches, in terms of how many inches per year, you can take a simple average, but in terms of growth rate, right? Because there's a time dimension, it's not static, it's, dynamic, right? In time, you cannot use a simple average. You have to use geometric average for the exactly the same reason I explained to you, because each year's growth, each year's height is the result of the successive growth from previous years, successively, right? And so now, then our next question. So how do you calculate geometric average? Here's this may you're gonna have to worry about this for now. I'll get to that. That looks quite daunting. So let me. So the geometric average is. We'll take slightly. Okay. I'll just. Come on. Okay, oh, this is better if I can write it. Okay, let me try this. Geometric average is equal to now future. Why doesn't it? Future value over present value over raised to 1 over n. It's not really. Well, why is it recognizing as? Okay, maybe I'll have to. 1 over n minus 1. Okay, this is wonderful. Where is it? Yeah, it's there. Okay, looks better. Yeah. All right, so this is the formula for geometric average. Okay. But, I will get, at this point, I'm just introducing the concept of geometric average. So further explanation about how this formula is, came about, how this formula is derived, or how it came about. That will be the future topic, right? And we'll discuss in the time value of money. But for now, that's how you calculate the. And then some people might wonder why 1 plus growth rate. Look, think about it this way. So how did we get to 180,000? Let me once again, let me draw it here. I guess this is not that bad using So isn't 180K, right, the result of, my handwriting is really bad, so please take it with some grain of salt, is the result of, first, the initial 2005 house value, which is 150, plus 150K actually. Where's the eraser? Okay. So 150K plus 30K. Well, what is it then? What is 30K? It's, we can rewrite it as 150K plus 20% of 150K. In other words, 150K dollars, right? Times 0.2. Isn't that right? 20% is 0.2. But this is very basic algebra, and some people instantaneously knew why this is, 1 point G, right? But for some people who hasn't figured it out yet, now, isn't that right? 30K is 150K times 0.2, 20%, right? Which is growth rate. Now, what is then in math? I've been telling you, math hates redundancy. And this is not the simplest form. And I mean, if it is redundant, it's not simplest form. So what do you need to do? You will have to factor out the common factor to simplify. Then it is 150K. My poor handwriting. My horrible handwriting. And then if you factor it out, in the parenthesis is 1 plus 20%. Let's call it G1. Or just G. Okay? So in the first year is G1. In the second year it's going to be G2, and so on. Now then, that's why it's 1.2, right? So this is what, if you open up the parentheses, in other words, you redistribute 150K. This times this, that's 150K, plus this times this, that's 150K times 0.2. Make sense? Everyone is good with that? All righty. So then that's what geometric average is about, and that's how it came about, and that's why we need to use geometric average when there's a time dimension, right, in a single variable. All righty, so okay, so that's it for today. I hope you have been able to see this Excel file. I don't know okay, I don't know if it was projected or not, but that's it. That's the end of this segment. I will see you in the next video.